Thank you for coming to the fifth day, the last day of the workshop. The first talk is by Daniel Deutch. The title is Towards Interpretable Data Science. Daniel, you can start. Thank you.
Thanks, Sudiba. So I will talk today about explaining computation. And as we know, machines make crucial decisions, even more so than they used to. And their decision-making is just getting more and more opaque. This means we need justifications and explanations. We need them for accountability. We need them to identify biases. And we need them for debugging. Multiple notions of explanations have been proposed, and some are actually widely used in the industry for machine learning. I'll talk about two of them. One is based on Shapley values, and the other is based on counterfactuals. And the main theme of this talk is that explanations are needed throughout the data science cycle. So what is the data science cycle? Typically, people talk about a phase of business understanding combined with data understanding. That's an exploratory step, and I will talk about this briefly. Then there is a step of data preparation, which includes data cleaning, data integration, and so forth. Then comes the step of modeling, which takes most attention, although it is usually claimed that around 80% of the data scientist's time is actually around these parts that precede the modeling, and then evaluation and deployment. Now, in this talk, I will talk about two facets of interaction between explainable AI, between explanations for machine learning and databases. One facet is ML explanation techniques for DB tasks, borrowing the ideas that are successful in the context of machine learning, of explainable AI, and making them work for database tasks such as data explorations, old school querying, and cleaning. And the second part of the talk will talk about a different facet, which is using database techniques to support and facilitate machine learning explanations. I will briefly show how database constraints are useful when deriving counterfactuals for machine learning. And I will talk about our recent work on declarative counterfactual management. So again, I claim that explanations are needed throughout the data science cycle. And the field of explainable AI typically focuses naturally on the AI, on the model when evaluated and deployed. And there are two leading approaches. There are many approaches, but there are two leading ones. One is called feature attribution, where the idea is that we get a classification and we want to understand why. So the why takes the form of assigning some score to each of the features of the particular instance that we are now classifying. And this score should reflect the contribution to the classification result. And here SHAP is a leading tool. Companies are actually using it. I will mention what SHAP is. Actually, that's very useful. The other type of explanation that people are typically interested in explainable AI is based on counterfactuals. Counterfactuals are perturbations to the input, small changes to the input that change the classification results. And then it's not necessarily a change in a particular feature, but rather it's usually a combination of features that change the classification result. And these are complementary in nature because the first talks about the contribution of individual attributes, while the latter talks about the contribution of attribute subsets. And then there are many other approaches that I will not talk about, including approximating the model via a simple one, and other approaches that are out there. So the leading approach nowadays in explainable AI in the context of feature attribution uses a notion called Shapley values, which is a notion from cooperative game theory back in the 50s by Lloyd Shapley. And there it was defined as a way to fairly distribute reward among players. So if we have a finite set of players, and we have a game value function for sets of players, essentially any function that assigns a number to a given subset, we define the Shapley value of a player essentially as its marginal contribution to subsets which is multiplied by some coefficient, which is justified by the satisfaction of some axioms that I will talk about in a minute. So that's a notion, that's a function that assigns values to players in a game. In the context of machine learning, the game is the classification and the players are the features. And we are given an instance in the model and we wish to assign a score to each feature, which reflects its contribution to the game, to the prediction. And again, this score is based on Shapley values, along with some hacks that are needed to account for the fact that we cannot really talk about subsets of attributes in a model. So instead, we talk about subset of attributes completed by, for instance, the average value of the other attributes in some set. But the result in the end is that we get some instance and a classification, and the model output is 0.4. That's the confidence of the model in some classification result, for instance. And then we want an explanation. So this explanation takes the form of the age contributes 0.4, and the sex, for instance, contributed a minus 0.3. As I said, the notion of Shapley is justified by the fact that it satisfies some very natural axioms. Efficiency, namely the sum of the Shapley values is the sum of the game, is the value of the game. That two equal players that contribute the same to every subset actually will get the same Shapley values, and some other natural axioms, linearity, for instance. And it turns out that if one insists on these axioms, then Shapley values are actually the only way to assign values, contribution values to the game in a way that satisfies these axioms. So Shapley values are both theoretically justified and are very commonly used in practice, which means that we should at least look at them in the context of database tasks. And this is further justified by the fact that we know that queries, for instance, may be used for feature engineering. So take a look at this particular database of transaction and searches, and we want a feature that states that some user is interested in fashion. This feature may be engineered by some complex query, and then we get the feature. So Shap tells us that this feature of interested in fashion contributed a lot, but who knows how this feature was computed, and we want to understand further what goes on in the computation. So to this end, Lifshitz, Kimmelfeld, and other collaborators have proposed to use Shapley values for tuples in query answering, where the idea is that the game value function is the query result and the players are tuples. And if we look at the Shapley value formula and we use it for Boolean queries, so essentially the game value function is the query result. So if you look at a particular fact in the database, we look at its contribution to the query result with respect to each subset of the database. And if the query, for instance, is non-Boolean, then we can look at the residual query with respect to each output tuple, and it works the same. It allows us to assign the contribution value for every input fact with respect to every output fact. So Benny and the collaborators, they have initiated a study of Shapley values for database queries. And in the joint work that I will briefly talk about, we talked about computational aspects. Namely, we have identified, first of all, that provenance is very useful here. So just a recap on what is provenance, although I'm sure that in this room this is not necessary. So we have a database and we have a query, say, return all customers with overdraft events after 2006 or something like that. And we want to know why did we get a particular result. So a particular form of y is what's known as provenance. And in this setting, we have joined P1 with C1, and we could have also gotten this result by joining P3 and C2. So this is provenance, and provenance is actually very useful if you look at this formula where we want to compute the query result over subsets. Provenance is very useful here because it allows us to read the query results over subset efficiently from the provenance without having to reevaluate the query over each subset. So we know that the provenance is satisfied for a particular set that the query is satisfied for a particular subset if the provenance is satisfied for the truth assignment that assigns true to the variables annotating the tuples in S and false to all other variables. So then we can read these the Shapley values. We can compute the intermediate results directly from the provenance. Moreover, this leads to a reduction to sharp-sat, so that may be of interest in this workshop on logic. So observe that if we look at the circuit that represents the provenance, and then we look at two circuits obtained by setting either 0 or 1 to the particular fact we are interested in, F, then what we get here is that actually all subsets of the same size contribute the same to the formula. So we can actually take this out and compute sharp-sat k, which is the number of satisfying assignments with exactly k variables that are set to true. And if we know this number for CF equals 1, and we know this number for F equals 0, then we can actually compute the Shapley values. Of course, computing sharp-sat k for a circuit is a difficult task. And we know from the theoretical results by Benny and collaborators, we know the Shapley value computation is generally hard, and they have established a beautiful dichotomy result on when it is tractable. What we did in this joint Sigmod paper is to develop a practically efficient approach that first compiles the provenance into a circuit, then applies a second step of knowledge compilation of the circuit, and then applies the exact algorithm over the compiled circuit to compute the Shapley values when this is possible. Sometimes compilation fails or is too slow, and then we propose a way for an inexact computation through a proxy function which allows us to rank the Shapley the influence without actually computing the Shapley values. So very briefly, knowledge compilers, we've used them in this setting to compile to a particular form called deterministic and decomposable circuits. And we say that an AND gate is decomposable if for each two input gates we get that they do not share variables. And an OR gate is deterministic if there is no assignment that satisfies both sides of the OR gate. And for a deterministic and decomposable circuit, we can actually compute in polynomial time the sharp-sat k value for all k's, essentially via dynamic programming. The trouble is that, of course, we cannot always efficiently compile into a deterministic and decomposable circuit. Our experiments show that it works for somewhat of 85% of the output tuples for TPCH, and for most output tuples for IMDb, where the queries are simpler in a sense. So this we've implemented using C2D, and again, it works fairly well, but there are cases where it just fails. It times out or runs out of memory and so forth. There are a few more steps to make this work. For instance, the C2D expects CNF as input, so we need the Zeitin transform to transform into CNF. And there are all kinds of technicalities to address in this setting. And then we get this 85% for TPCH and 99% for IMDb. For these cases where the compilation is too costly or may fail, we can actually resort to ranking. Instead of computing the actual Shapley values, we can try to rank to decide which of the facts influenced more than the others without actually computing the exact Shapley value. And we do that via heuristics, which essentially, instead of looking at the CNF itself, we look at the proxy function, which essentially, if you think about the conjunction as a multiplication of the value function for the different clauses, we look at the sum of the clauses. So intuitively, we look at how many clauses were satisfied. And thanks to the Shapley linearity property, to compute Shapley values with respect to this function is much more efficient and can be performed in linear time. Now, of course, what we get is not the Shapley values of the real function. It can actually be arbitrarily off. But it turns out that in practice, and in many cases, what we get here is actually very close to the real values. For instance, the precision at 5 is typically almost 1. We can also propose a hybrid computation, which is what we propose in practice. Essentially, start by running the exact computation algorithm, and if it completes successfully in under t seconds, just returns its results. Otherwise, terminate the exact computation, give up on exact values, and resort to this ranking. And this is an approach that's actually very effective in practice, because what we have observed is that if the algorithm succeeds, it typically succeeds quite fast, like in 2.5 seconds. So after this threshold, we can just resort to a ranking without guarantees. When we have this ranking or a computation of Shapley values, depending on how the provenance looks like, we can essentially combine it with the classical provenance views, because you see, like I said before, there is, I talked about it in the context of counterfactuals, but it holds also in the context of queries. Shapley values, their power is that they allow to quantify the result of each individual contributor. So they're very simple in a sense to visualize. We can see that the fact that Alice bought this item was actually very influential. So it's easy to communicate the explanation. On the other hand, it's very partial, because this fact did not stand on its own, it stands together with other facts. So what we have proposed, we have developed a system called ShapGraph, which actually allows two views together. So we visualize the provenance graph in the standard form of a circuit, but we also highlight in each for each node of the graph its individual contribution. And the users can actually go back and forth between these views of individual contribution and joint contribution via provenance graphs. So that's another view of the system. You see the circuit with lots of nodes, but then you can also see, according to the color code, you can see which nodes contributed the most, and you can actually hover over them and see what their contribution is. So that's a mixed view of joint and individual contribution. All right, back to the data science cycle. So we talked about data preparation in the sense of feature engineering that may be used via querying. There are other facets of data preparation, for instance, data cleaning and data repair. And again, that's actually something that's very, the data scientists care a lot about. We have developed a system called T-Rex that uses Shapley values to quantify the contribution of each cell and constraint to each repair. And this can work on any black box repair algorithm. We've used it in particular for HoloClean, which is commonly used for data cleaning. Of course, the main issue is performance. Shap itself is not optimized for this kind of task and does not scale, so we needed to develop some pruning heuristics and to use them in conjunction with sampling. But the end result is that we get a database and we have some rules that it violates. So then HoloClean or any other system recommends a fix. And we want to know what contributed to this fix. So T-Rex can actually say, well, this cell contributed the most, in this case, to this particular fix. So we can know that this was the main reason for the fix, And of course, it's a marginalized view in the sense that we marginalize the contribution of each individual cell, while in practice, multiple cells contributed together. So it's complementary to other approaches. If we go further to the data understanding phase of the data science cycle, here people typically talk about exploratory data analysis. So what is exploratory data analysis, or EDA? It's a common preliminary step in data science, which involves looking at different views of the data. And it's not necessarily with a particular analysis goal in mind. You don't have necessarily a query in mind, but rather you're just looking for insights, which is a very fuzzy concept. And then actually data scientists regularly publish the notebooks that record the exploratory steps and the intermediate results. And that's something that other scientists are interested in, because if they look at the same data set, they want to know what insights others found there. And there are two challenges for the first part. For finding the insights, that's hard, of course. But then also understanding the notebooks that others published is also hard. So we've developed a system that explains data exploration. You can think about a particular example where you have a data set about flight delays that's analyzed in the notebooks, and then other analysts look at this notebook and try to understand what was going on. So our systems automatically generates explanations for the interesting parts of the views. Now, what's the interesting part of the view? That's, of course, debatable, but there are some standard interestingness measures that are typically used actually for recommending steps in EDA, such as is the view diverse? Does it exhibit some diverse phenomena or exceptionality, and other kinds of interestingness measures. So what we've did here is, again, we looked at Shapley values as means to quantify the contribution of each tuple to the interestingness measure. Essentially, not just saying this view is interesting because it has high diversity, but rather what contributed to this high diversity. So we have this database of flights, and the analyst filtered the table to find flights with duration that's greater than 90, and they got something, and they published the notebook, and that's it. But we want to know why. What was interesting in the generated view? So again, we have this, like I said, these interestingness measures. So we compute multiple interestingness measures for each view, those commonly found in the literature. And then we find the top k elements that contribute the most to the interestingness of the view. And we use the Shapley value to rank the contribution of each element. And then we have some more gadgets, for instance, some hard-coded natural language patterns. We can actually auto-document notebooks with comments such as, well, the major deviation occurs on this group, where this attribute value changed from this value to this one. And we can actually embed this in the notebook itself. So we see the filter operation, and then we say, well, the view shows high exceptionality. So that's the interestingness measures that we get from previous works. But we further specify that specifically the major deviation, and that was the major contributor to this high exceptionality. Okay, so far we've talked about ML explanation results, techniques for DB tasks, specifically taking Shapley values all the way back in the analysis. And in the next few minutes, I want to talk about another aspect, which is using database techniques for machine learning explanations. Here, I want to talk about a different approach, which is that of counterfactuals, which is, as I said, are perturbations to the input that change the classification results. And like I said, it's complementary to Shapley values. So counterfactuals, actually, there is a recent survey that cites hundreds of works on counterfactual generation in the context of machine learning. It's a very vibrant area of research. It's highly useful both for explaining individual predictions, which was the use case that I talked about in the context of SHAP. So we have a prediction, we want to understand why. We can either give quantify the contribution of each individual feature, or quantify or say these features together were very influential. On the other hand, it's typically slower to compute in this use case than SHAP, which is why SHAP is typically preferred for this use case. On the other hand, it's highly useful for explaining the model as a whole. And I want to show you two or three rather very common examples. So the first is LIME. I imagine that some of you heard of it. That's a work from University of Washington. And the main idea is that one samples perturbed instance around some instance X of interest. And then these are weighed according to their distance. And we retrieve the predictions on these perturbed instances. So some of them are counterfactual, some of them are actually perturbations that behave like, that were classified like the original instance. Now, we learn a linear model that approximates the model well in the proximity of this particular point, not necessarily in general. And then we highlight, for instance, superpixels in the context of images with positive weights towards this class in the linear model. So then the highlighted superpixels, the highlighted part of the image, actually highlight what was interesting and the parts of the image that were most influential in the decisions of the model. So that's one way to use counterfactuals to analyze the model as a whole. There's another work called Certify that actually looks at the magnitude of the required perturbations to quantify the model fairness. Essentially, the idea is that if a particular group, a particular minority, for instance, not only is classified more negatively, but rather needs to change more to be classified positively, then that's a sign of unfairness. So if the magnitude of the minimal counterfactuals, if the magnitude of changes that I need to pass the classifier is higher for this particular group, that's called the burden in this work, then this indicates unfairness towards this group. And then there is this area of research called algorithmic recourse, where the idea is to find not only counterfactuals, but rather actionable counterfactuals. For instance, if you raise your salary by 100K, then your loan request would be approved. So these are three ideas on how to use counterfactuals for model analysis. I claim that database constraints are actually very useful in each of these scenarios. And the point is that these counterfactuals are often hypothetical instances and not necessarily real ones. And to be of interest, they should be realistic, right? So for instance, a counterfactual instance that changes the country but keeps the city intact is not a very useful recourse, telling you stay in Tel Aviv but move to the USA. That's not a very useful recommendation. And it's also problematic if you want to use it as a training instance. And that's the kind of information that we can get from database constraints. We can know that that kind of counterfactual is actually impossible. So we have incorporated in the computation of counterfactuals, we have incorporated different kinds of database integrity constraints, such as domain constraint, check constraint, conditional functional dependencies, and unary denial constraints. And we've derived them for the same databases that people use in the machine learning training. And then we've developed a fairly simple algorithm which essentially tries to perturb, tries to find a counterfactual. If this counterfactual actually violates the constraints that are marked here in this yellow rectangle, then we do a projection. Once we did the projection, then maybe we are back to this blue area that we started with. We wanted a counterfactual that would lead us to the red one. So then we need to perturb again and project again. And that's completely heuristic, but in practice, it leads us after a small number of steps to a point that's actually both in the area of classification that we want and in this rectangle, meaning it's useful, it satisfies the constraints. So I'll skip the details of how that's done, and I'll just show you that actually when we use constraints and retrain a model, we get better results than just retraining it on counterfactuals that ignore the constraints.
Daniel, could you wrap up in 1 or 2 minutes?
Yes, yes, absolutely, absolutely, yeah. So the last thing I want to show, and that's the perfect for this 2 minutes, is our recent work on counterfactual databases, and that's another example of how to use databases for machine learning analysis. So the point here is that counterfactual generation is actually computationally costly, and it's computationally costly, especially when it's constrained, and especially when we need many counterfactuals for many instances, like we do in this scenario of model analysis, rather than explaining a single prediction. So we have developed a system called the CFDB, which includes a declarative language for CF-based analysis. It allows to interact with a CF generator oracle, so any one of the algorithms of the 100 algorithms that I have mentioned before, and optimize the trade-off between CF generation and reuse. Essentially, the idea is that if we have already in the database a counterfactual that's in the proximity of the instance we are interested in, we can avoid calling the counterfactual generator. And we can also anticipate this and reorder the calls to the generators so that we will have counterfactuals to reuse. So that's a simple example, and I'll wrap up with that of CFQL. So we can specify which predictions we're interested in this case, false negatives, ones for which the ground truth is accepted but the label is rejected from the training data. And we can specify what kind of counterfactuals we're interested in this case, counterfactuals that keep the home status intact, but increase the income. The semantics is that then we compile the constraint into Boolean expressions, find counterfactuals that satisfy these constraints, and store the results in the database. Once we have these in the database, so we have in particular these instances corresponding to these predictions, which are false negatives, we can actually know what kind of counterfactuals we are interested in, and that's actually via C tables. So via compiling the query into using the C table algorithm to evaluate the query, we can reach a Boolean condition such as the home status should be on and the income should be greater than 80. That's one counterfactual we're interested in. And another one is where the rent, the home status is rent and the income is greater than 60. So that's passed on to counterfactual generators. There are many of them that know how to get Boolean expressions as constraints, and we get a result. One other example is to use a CFQL for certify. Again, here we're interested in changes that do not change the race and gender, but rather change other features. And with under the hood optimizations, we're able to significantly speed up the CF-based analysis. In particular, we can get the same conclusions as certify much faster if we, by controlling reuse threshold, which is a user-controlled parameter, deciding whether to reuse counterfactuals rather than invoking the counterfactual generator again and again. So just to conclude, explainability is extensively studied in both the database and machine learning communities. We need explanations for different components of the data science cycles, and these solutions should interact. The Shapley values that are useful for machine learning may be useful for attribution across the board. If we have database constraints, we should account for them when generating machine learning counterfactuals. And if we have explanations and we have a database, we might as well store the explanations in a database, analyze them, and use the beautiful techniques from declarative databases to optimize the analysis. Thank you.
Is there one very quick question for Daniel before we move to Amir?
Hi, Daniel. Thanks for the talk. Do you have any idea whether maybe Shapley values could be extended for queries with aggregation? Do you think there's any hope? Or
yeah, so Benny worked on that.
Could you, Daniel, 1 second, please. Could you stop sharing and Amir can share and then you can answer?
Yeah. So aggregation is a very interesting question. Benny had some beautiful theoretical results about it. Maybe he wants to answer. And I don't think there is actually a practical system implementation for Shapley for aggregates. Correct me if I'm wrong, Benny.
Yeah, no, there are theoretical results that extend what we have on Boolean points. I'll talk about it. I'll answer the question in my.
Okay, let's discuss more when we have the discussion session.